graduated from with his PhD from this university in 2001, and since that time he actually made a very good path to a wonderful career. Started actually with free-scale semiconductor in Texas, and then after that he moved to IBM to actually coordinate the consortium of 7 companies in I think Hudson Valley.
Mm-hmm.
And after that, he's a great traveler too. He decided to move to IMEC. IMEC is also a big consortium for semiconductor, actually the biggest consortium for semiconductor in Europe. Okay, where he was actually vice president of IMEC, I think for research and development. Okay, but after some times in Belgium, where I'm from, but I have nothing to do with it, because it's what in the Flemish part.
Yeah.
So he actually moved to Singapore, which is in fact his own country, where actually became a professor in the Department of Electrical and Computer Engineering at National University of Singapore. But at that time, he was also director. You can see this, a director for Industry Partnership, Office of Deputy President for Research and Development. He's also director of a group on flexible electronics, and also co-director from A-Star Syntec collaboration with National University of Singapore. So today is going to talk about this equation there. This is the first time I saw this equation, okay, where novel material plus novel integration equals novel electronics. So he's going to talk about it. But before that, I have, on behalf of the department, to give you this nice gift.
Thank you.
Okay,
thank
that you can open after the.
Yes, I will do that. Thanks. All right, thanks, Jean-Pierre. So Jean-Pierre was my PhD advisor, if you're wondering. Thanks for spending this afternoon with me. I'm jet lagged, so I may fall asleep when I'm talking. So thanks for inviting me to give this inaugural lecture as a distinguished speaker. So the only reason why I have so many titles is because I do a lot of other stuff besides research. But today I'm going to focus on research and technology trends. I chose this title because it's a cop-out title. It basically says I can say anything I want, effectively. So it's very general. So the intent of this is really to give you a survey of the trends in the industry in terms of advanced materials and advanced electronics, and also how it actually changed my path, my career in research. Okay. Let's see. Okay, so the first thing, a few message. There's only 2 things to remember in this whole talk, which is one is convergence, first thing, which is, I think you know this word, it's basically the merging of distinct technologies, industry, and devices into a unified whole. It actually just means coming together of different things, okay? And one of there are now basically a few trends, global technology trends that you've seen that it's the result of convergence. One of them I think you may already be aware of, which is autonomous transport, autonomous vehicle, which is a convergence of data analytics, machine learning, AI, IoT, and robotics. Okay, and the second example of such a convergence is bioinformatics, which is convergence of data analytics, biochemistry, and computation. Why you can see over here that because of computation and electronics, basically these 2 fields, effectively robotics, which in the form of autonomous vehicle, and genome sequencing, which went from $100 million to sequence the whole genome, drops down to 1,000 and eventually down to 100 within a period of 14 years. So these accelerated progress results from basically different technologies coming together to solve the problem. Right? Now, in order for convergence to happen, the second thing that I would like you to remember is integration. All right? The integration is the work of actually uniting different parts. Now remember, integration doesn't mean convergence, but integration, if the sum of the parts, if the whole is greater than the sum of the parts, then you have a successful integration. We're bringing new functionality. And what an example of a highly successful integration, which also reflects a convergence, is a smartphone. So this is iPhone 8 Plus stripped to its components. And it's not just one. You notice that this is a system. It's advanced, one of the most advanced smartphones, but it's not necessarily made up of the most advanced components. In fact, it's made up of a heterogeneous mix of components. So you can see there digital processors, memory, power management chips, sensor, display, and micromechanical machines. So it's a system. So the convergence of a phone, a communication device, a computational device, the sensors, is made possible by an innovative integration of these components. In this case, the different technologies coming together. Okay, so those are the two things, and I'm going to talk about next. That brings me to new technology convergences, right? And that's the trend. So we already talked about this. So application technologies result smartphone, and I think we see new areas are emerging, which are due to convergences. For instance, wearable technology, precision medicine, neuromorphic computing. So the first integration is actually resulting from Moore's law. Okay, so this is very familiar for every person that's doing semiconductor. For instance, today at 2018, we're talking about 7 nanometers, so single-digit nanometers. And eventually by 2022, we're down to 3 nanometers. And this is all to do with integration of transistors and interconnect, right? So the second integration is system scaling. You see that going forward, instead of scaling just transistors and wires on a chip, we'll be scaling multiple chips on different packaging to make new systems. And then finally, the third thing is form factor scaling. So how do we make things thinner, more pliable, easy to pack into tighter spaces, right? So what I'm proposing is that these independent integration will converge at some point. You're already seeing two of them I'm going to talk about next, which is the Moore's law scaling and system scaling. I think the next one will be form factor scaling, which requires additive-based manufacturing. I'll touch upon that. So we're leading towards heterogeneous hybrid in electronics going forward. All right, so let's talk about Moore's law first, right? So before and after Moore. So everybody knows that today we get this wonderful stuff about our chips performing better and better with more and more transistors. Is due to the fact that we could scale for every generation 50% smaller, basically in terms of area per transistor, which gives us 2x the density. Now, but what's interesting is to look back in time before that happens, right? So 1904, that's when the vacuum tube was sort of invented, and then comes Bardeen, Brattain, and Shockley, the first transistor. I think Bardeen is one of the icons here, and that happens sometime in the 50s, in the early 50s, late 40s, early 50s. But nothing happens till actually Robert Noyce and Jack Kilby. Kilby is another alumni here in Illinois. Figured out how to integrate solid-state components into circuits. And you can see that happens sometime in the late 50s and early 60s. That's when Moore's law happened. So transistor was invented, but that did not trigger Moore's law. That did not trigger the advancement, the accelerated advancement in electronics. It's the invention of the transistor coupled with the convergence with integrated circuits. That means the ability to process them in a planar way led to the acceleration. Right? So the key message here is integration is very important. And so how to put things together in a way that accelerate density and functionality. And so today we're continue pushing the cycle, and we have accelerated innovation going from 65 nanometer to 14 nanometers. Okay. So back in 2011, an inflection happened, and the transistor just got flipped on the side. I think some of you may have known this, some people may not have. But most of the technology since when Robert Noyce and Jack Kilby both have worked on are all based on planar technology. That means everything stays flat. Process comes from the top, right? But sometime in 2011, the transistor went from being flat to being on its side, right? And that's the FinFET that you see on your right-hand side. Now, what's so special about this? Well, first of all, physics-wise, the transistor no longer conducts on the surface, it conducts on the side wall of the device, right? So the material properties have changed. But there's a reason for this change, is because this transistor does a lot better than the planar. And it's beyond the scope of this lecture to explain to you why that is, but electrostatically it's better because it's a thinner channel. But more importantly, it's easier. It is the only easier way to make it in such a high density way, right? Because you can obviously make a thin channel device flat, but why did they make it upright? It's because that's manufacturably the easiest way to make this. And now that change also came about because process technology has reached a pinnacle where we can actually do it. Okay, so to give you an idea of what that means, so this is the FinFET. When you cut it cross section, this is transmission electron microscopy. It's an image from Kazat Mystery of Intel, 2017. So 22 nanometer was the first technology in 2011 where the FinFET was introduced. It's a pyramidal or triangular shape. And then in 14 nanometer, it got skinnier and thinner in 2014. And today, in 2018, they released the 10 nanometer technology, and the fins are like 5 nanometer thick at 53 nanometer tall. So this is close to a 10-to-1 ratio in terms of height aspect ratio, right? So now the interesting thing is these process control were never possible before, and to control nanostructures to this level. And I'll talk a little bit about what will come next. But effectively, all these structures cannot be printed by lithography. They're sublithographic. So think about it. So how did they get these patterns in the first place? That's the interesting question. They cannot be printed. They're derived, actually, from printed features. They are not directly printed. So back in 2015, I worked with my team on the next generation. This is the fin that's going to come in 2020. Okay? So these fins, you can see, they are only about 2 to 3 nanometers across. And they are done regularly spaced. No change, space between them. Okay? If you compare it to something, so this is about, each fin, if you can look at the top there, the inset, is only about 10 to 12 atoms thick. Right? So they're not deposited, they're all completely etched. Right? And if you were to look at a comparison, a DNA diameter is only 2 nanometers. So this structure, which we can produce by billions, is at the diameter of a DNA molecule, effectively, a chain. Okay, so how is it made? Well, it's sublithographic. Obviously, you can't print that. There's no printing technology that could directly print structures like that. So they're made by something called multiple patterning. And the way it works, in a nutshell, so you print some feature, the blue feature, we call it a mandrel. And then you create spacers from this mandrel by using deposition. Very accurate, because you can control how thick you deposit. Right? And this deposition thickness can be below the resolution for anything that you can print with light. And then you use these, you sacrificially remove the blue parts, and then you use the spacers that are left behind to create the next set of mandrels. And then those mandrels create the next set of spacers, and then those spacers create the final fin. Okay? So this is self-aligned quadruple patterning. So the chip that you have today, if you have an iPhone 10 or iPhone 8 Plus, the 10 nanometer chip in there contains billions of devices that are made like this. So this is beyond what can be printed lithographically. Okay, it's derived. But of course, this is an interesting way of doing it. That means we no longer depend on just printing alone to get down to small features, right? So it's no longer a obstacle to Moore's law. So interesting. Now, so what is the ramification? It's not enough. The fins don't scale forever. we want to go beyond 2020. We want to continue Moore's law because it brings value. Okay? So the next generation, what comes out of the fin are wires. Okay? So the way we do it is you use new materials now in a new integration form. So now the fins, instead of made of one certain kind of material, is made out of superlattice of silicon and silicon germanium. Okay? And these things you build just like the fin, but you sacrificially remove those silicon germanium. So this is actually peering into the channel of the transistor on the side. You see two tiny wires that run on the side. Right? So those are silicon wires after the silicon germanium is removed. So what does this technology require? Well, this technology requires precise epitaxial deposition of these superlattice, because these are finally going to be your wires and spaces, right? So you have to control it. Second, you have to etch these with atomic precision, because once you etch this, and you can't touch, it's like playing Jenga. You have to remove something, leaving behind the rest, not touching it. So it's selective removal, right? So you know how to do that. And that gives you a structure like this. So this is a cross section that looks two wires stacked on top of each other. And precise control, 8 nanometers across. Billions of transistors on a chip. So to say that, basically in terms of semiconductor process technology, we have come to really a pinnacle of control using material and structure down to the atomic, effectively the atomic scale. And you'll be surprised the next few things that will come along the way. Wires that go vertical, for instance, highly controlled, right? In fact, at some point we were working with Professor Xiuling Li over there, working on those vertical structures in 3.5, right? So with that, we come beyond silicon. So there are materials that are there that, that 3.5, germanium, those things that are not silicon they actually bring new value to the system. So in this case, for instance, if you can do 3.5, you get access to a direct bandgap material. It has much higher transport mobility. But in this case, we want 3.5 to be in the same size scale as the fin. How do you put a material with at least 8% lattice mismatch in the same volume as those tiny fin? That's what the challenge that I worked with the team at IMEC. So the way you do it is you build a fin, okay, in silicon, and then you remove part of that fin, and then you regrow it with 3.5 or compound, in this case indium phosphide, compound semiconductor. So basically now you just basically use the fin as a mold to put in new material. Effectively, that's what happened. Now, of course, it's not that simple because you're putting materials that are very, very disparate in terms of lattice constant, and then you're going to create defects. How to engineer those defects is the work of art that we have to figure out. And the way it's done is we intentionally create defects where we don't care, and then use those defects to trap the defects that are formed due to the lattice mismatch. So again, I'm not going to go into details of that because that's beyond the scope of this lecture. But the key message is that now we are in the phase of engineering defects. So things that we used to not want, now we basically want it, and we want to put it in certain places so that it can accomplish certain things. So again, it's material engineering that we need. All right? So now that's all good, but it comes to an important problem. And the problem is actually cost versus value. Now, we're doing a lot of cool stuff, but is it cost effective? And does it create value? And so this is a chart that is an analysis of the technology to look into Moore's law scaling and what the cost and value would be. So if you look at on your left, this is 28 nanometers. The 10 nanometer we talked about, 14 nanometer we talked about, right? You can see that cost, if you partition it based on the front end cost, which is the cost of building the transistor, and the back end of line, which is the cost of wiring it using the interconnect, the wiring is about 75% of the total cost. And that cost is rising rapidly. And the reason for that is very simple. So as I described to you previously in the fin, the fins are, to get each layer of fin or each layer of structure, there was at least 4 or 5 patterning steps. In the old days, you just have to print them with your contact aligner, you print them with your lithography tool, you're done. That's your pattern. Now, in order to achieve that, you have to print, you have to deposit, you have to etch, you have to print, deposit, etch. That multiple steps basically incur cost. And that's multiple patterning cost. And you can see that this cost basically drives up the wiring. And the reason for that, if you need to do that for every layer of wiring, that's a lot of steps that you do. You always have more wiring than transistors. True? Because each transistor have 3 contacts at least, minimum. And you have to connect all the transistors together, you have more wiring. That's Rand's rule, really. Now, that increased wiring also creates another problem. And the problem is parasitics, right? So ultimately, we want to switch these circuits. We make them denser, but we want to switch them at lower energy, at higher power, at higher speed when we scale. And if you look at the parasitics, which is really the load that slows down the switching, you can see that as a function of technology node, the gate capacitance, which is the switching of the gate itself, versus everything else, as you switch a transistor, everything else is also 75%. So effectively, you're wasting all your energy switching something else whenever you're switching with that transistor, and that something else is all that wire that is coming down like a forest or vines connecting to your transistor. That's the problem. So this is the real threat of Moore's law. You know why? Because who wouldn't want a new chip that performs better and costs the same? It's only when it costs a lot more and doesn't do the same work that becomes the problem, right? That's the undermining factor to Moore's law. So that's the true issue today that's faced by the industry today. And how to solve this is still not entirely clear, because several approaches from system design, system tricks, to new transistor, to new architecture are being explored. So, but it's not new. This is a chart that basically highlights one point. There's no longer one type fits all kind of device on a chip. As I mentioned before, it's all about opportunistic scaling, right? Because since, like I say, the transistors are overloaded with wires, so that means that certain circuits, please don't load them with so many wires. So some devices allow it to leak more but runs faster. So there is a way to trade that off, and system needs that freedom. So this is not new, because if you look at the early days, circuits used to have one VT device, single type of device, no I/O even. The device can be I/O, can be a logic switch. Circuits were much simpler. As the circuits get more and more complicated, we get more and more types of devices. SRAM has its own device. You have multiple threshold voltages. I/Os have several different types. And more and more these devices basically get increased in variety. So that means the need to integrate them all onto the chip is necessary, right? So now you need techniques to integrate them all onto a chip. And that's the reason why. So in order to enable system to basically scale opportunistically, that means that it is loaded, but I turn off some of the time to save power. I run faster when I need to. I save energy. Basically system needs new devices that allow the system to do that, right? And hence more and more different types of devices happens. And this trend of component specialization is happening. And it's the key motivation for heterogeneous integration. Ability to integrate new devices in that does specialized job. Right? Makes sense, right? Why would anybody be introducing new devices in if it costs more and doesn't do extra work? So that's the motivation. So that's one of the key trends going forward. And you hear this, right? In neuromorphic computing, people are talking about introducing memristors. Previously, they were using SRAM, but memristor could do the analog storage better than SRAM can, for instance. All right, so that brings us to the second trend. So in order for heterogeneous integration, basically it leads us to multiple chip packaging, heterogeneous integration in that sense. Let me explain that a little better. So today a chip may do a certain thing, but we want the system to do multiple things and to optimize going. So not only at the level of transistors we're getting heterogeneous integration, but today at the chip and die level we are doing that. And you do that through this integration on the package. And it's called system scaling. All right, so these are two charts, one from Global Foundries and one from Intel, basically saying the same thing. Right? So on the Global Foundry chart it says there's miniaturization, which is Moore's law. On the horizontal are diversification. So these diversified components, RF, non-volatile memory sensors, and then there's this convergence towards the middle, system in package. How do you bring things like sensors and memory and biochip stuff together with advanced CMOS? And that's where the value is. And in the Intel case, they talk about basically a new platform where they can get different technology all on the same die or even the same substrate, from 10 nanometer to 14, and you can do that by bridging this. So so the next part I'm going to talk a little bit about that. So this is the example of SK Hynix high bandwidth memory. It's interesting. You know why? Because one of the biggest problems in electronics today is the memory excess energy. So you can imagine if your data processing always have to fetch data from your hard drive, you never get anything done. Okay? So data needs to be moved closer and closer to where the computation is to speed up the processing and reduce the memory access time. So this is one way to do it. This is the processor, and you stack a whole bunch of DRAMs around it. And now this is not one slice of DRAM, but a high-rise stack of DRAMs, all on an interposer, which is like a super chip. Right? And so this is how it's done. And this is already in the market. Going forward, any applications that need massive amount of computation, massive amount of memory, and need fast access would look into this high bandwidth memory, HBM. All right? So the HBM, it's a very interesting technology. This is, again, an SEM image of that. So remember those stack of DRAMs, those are these, right? DRAM dies. It's stuck onto this super chip, which is an interposer, and that is connected to a board somewhere. Okay? The interesting part to highlight is that these structures here that kind of permeate and perforate through layers of DRAM is something called a through silicon via. It's a giant nail, basically. Okay? So I'll show you in a bit what it looks like. So that's what it looks like. So this is a 5 micron by 50 micron deep through silicon via. So it cuts through the substrate. It's thinned down, obviously. And that thing punches through the substrate and basically connects to the next level below. Okay? So this is work that I've done with my colleagues at IMEC, comparing the size of this giant interconnect, right, TSV, next to fins. So these are the fins that we talked about previously. This is that big structure on top. Okay? So it's huge, the size disparity between this. And the process to develop this is also very different. You can also imagine this thing here is going to affect this tiny thing on the side. But the technology is there to make sure to figure out how do we integrate this thing, which is humongous, next to these tiny things on the side. Right? How to exclude them. And that technology today exists. But that's interesting because it brings forth the concept of 3D stack microsystems. So this is a roadmap by my colleague in IMEC that talked about ways to combine and stack circuits. Okay? So you can stack it in many different ways. But if you look at just from a size scale point of view, obviously you can take two chips and just drop it on top of each other. Right? And so that size is in the tens of micron in pitch, because that's the rough feature size of those circuits, blocks of circuits, basically. You can obviously stack them at the circuit level, block level, and you can go down to maybe down to the 0.5 micron level. And if you can even stack transistors on top of transistors, and that will get you down to the 100th of nanometer alignment, right? Because here you just need to align two giant pieces of silicon. Here you need to align two giant blocks of circuits. Here you have to align two tiny transistors, right? But the level of integration is obviously different, right? Because here you're going to get increasing integration density. but the technology required to do that is completely different, right? From here to here to here, it's about alignment, about different ways of processing. I'm going to talk a little bit about that. And so the most extreme form is, as I mentioned, is the transistor sitting on top of transistor. So the circuit effectively can be vertical at the smallest level, right? So this is there are many names for this. One is, some people call it monolithic 3D, 3D IC, sequential stacking of the transistors. So this is actually from a paper from Ledi in France. They talked about this technology. So you can see there, two transistors sitting on top of each other, connected vertically, okay? And then conceptually, you can build this forever, one after another, right? So now your layers go vertical, right? And the transistors and the interconnect no longer have a front end and a back end difference. Everything sits interchangeably between the layers. But there's a problem. There's a problem as follows. In advanced interconnect made out of copper, the processing temperature cannot be greater than 400 degrees C. And the reason for that is because copper will out-diffuse into the low-K dielectric layers and mess up your entire circuit, right? Transistors, like at least silicon, likes to be processed somewhere around 800 to 1000 C, because that's where your dopants are activated, and that's where your defects are annealed. So there's a problem. If you want to build transistors on top of interconnect, which is what the dream is, basically the interconnect has to be able to tolerate higher temperature, or your transistors have to be processed at much lower temperature. But processing transistors at lower temperature basically reduces its performance, because you have defects and the dopants are not activated. Okay, so that's a one major issue that people are trying to overcome. So here comes the nice work from Stanford. They had a Nature paper where they looked at stacking of systems. Okay, so conceptually they want to do the same thing I talked about. You want to stack layers and layers of logic. You want to stack layer sensors on top. And that paper, they talked about this eNodes, or this neuromorphic chip that they're trying to build, where they have silicon logic at the bottom, and then carbon nanotubes logic on the top, and RM and all that. And they managed to do it at least in a prototype conceptual base. Okay. So what's different? Why can they do that? And the reason for that they can do that is because carbon nanotubes are not silicon. They're actually additive-based transistors. They are actually processed at a much lower thermal budget. They are grown at a high temperature, but they are transferred in onto the chip itself. So they are not like silicon, where it's processed on chip, where you need to subject it to high temperature, and hence it doesn't affect the. So I had discussions with Subhashish Mitra and Philip Wong, which they did this work, and that's the main thing. They couldn't be able to do this with any other material. If they try to do it with polysilicon, the devices would be horrible, right? And you still need some temperature to anneal. So carbon nanotube offered something different. And these type of devices are not unique, because if you look, for folks who are working on 2D materials, that's what it is. So 2D material has the same thing. You can basically, if you can do large area, 2D materials are these materials where they are fundamentally, cousins of graphene, for instance. They're two-dimensional materials with little defects in principle. They exist, transport layer do not need any intrinsic high anneal for doping, activation of dopants. Can happen in stacks. You can put them in the back end without any problem. Same thing. You grow it somewhere, large area, transfer them onto silicon, and then process at low temperature. Right? So this is one very important application for 2D materials, and that's why it's interesting to look at that. Right? So previously in my group, we were looking at growing this. So it's not, the problem is that they are not easy to grow at large area. So you can flick them off native substrate, but if you want to do it on an entire wafer, it's another story. So here are work that we did, and clearly the defects and stuff, there are a lot of physics and a lot of material science that go with it. But one of the key learning is that they also need to be grown at high temperature. And they need to be grown with substrates that basically help them align in their atomic order. So that means that we have to grow them somewhere else at high temperature and transfer them in also. Okay? So this advanced substrate and this advanced form of adding layers by layers drives new trend. But it also has the same, or I won't say same, a similar problem with cost and value. Okay? So in the transistor, as I mentioned before, the issue is patterning. You basically, as you scale down the circuits, you scale up the density, your patterning basically creates more costs for you. And then the value is degraded because you have parasitics that drags you down. So you're not getting full value. Okay? Now, there's also an issue with advanced substrates, right? So now we try to solve the problem by stacking chips together. Yes, not getting enough value from the transistors. Let's do this. We're going to stack different chips together and create new value from it. But then it has a cost implication. So at one end, you have 3D stacking, which is expensive, right? Because there is actually no essential reduction in die size. Nothing is shrunk, actually. We just added a whole bunch of value and added a whole bunch of steps. So no reduction in cost. It's a problem, right? So not all applications can tolerate it, right? If I tell you that I stack for you a whole bunch of chips to make your iPhone 12 much more powerful, but you're going to pay twice as much, you say no way, right? So now you can go back to the board. It's cheap, but the integration density is low. So people say, well, there must be a sweet spot. There may be a new convergence for system level scaling. What would that be? How do I lower cost and then improve on the functionality? New technology needs to come in, right? So that brings me to this chart, which is an interesting chart. As I showed you before, if you look at the iPhone, I'm taking the iPhone 8 Plus as an example again to beat it up some more. You can look at the bill of material. Okay, so bill of material basically says how much of the components people think it costs. If you look at it, right? So this is ranked. So the most expensive part of your iPhone 8 Plus is your display. So don't break it. It costs about $52. Okay, out of 500 or something, right? And then the second most expensive part, which is very interesting, is not the chips. It's the mechanical structure and the interfaces. Okay, it's that casing and all that stuff that's mechanical. All right. The third one, not too surprising, is the camera. Right? Every iPhone commercial now talks about how great it takes pictures, not about how great it makes a call. They don't even tell how great the computational power is anymore. It's all about I can take a great portrait, right? So camera, very important. And the fourth, memory. So if you take pictures, you have to put it somewhere. So that's the memory, right? No memory, you're not going to store pictures. That's going to be very, very frustrating, right? That's why so these four things, okay, and then trailing behind your apps processor, you have the RF, you have the baseband. Look at the sensors, $6. That's it. So sensors are cheap, but they are all important. So the value is important. The value is the integration of these, right? But the cost of these components are different. So these four parts is really an opportunity. If you innovate on these four things, you innovate on the most costly part of the system. Doesn't mean that you don't work on the rest, but they are actually part of the whole. So, but those are the most lucrative part to work on. All right. So the point to make is that mechanical structure, MEMS, taptic engine, and stuff like that are pretty substantial. Even older technologies also cost pretty substantial. So not most advanced. So the phone may be the most advanced thing, but not everything is the most advanced in there. And it's the integration of all. But there are four components that are definitely very, very important. And that's why you see globally a lot of memory foundries are setting up. Why? Because it's lucrative. Everything needs memory. Display is a Going from backlighted LEDs to OLED, big deal, right? These are all things that become important, but mechanical structure. So the board, the casing, that's an interesting part to innovate on. So that brings me to the third part, which is form factor, right? That is the part to address the mechanical part, the substrate, everything, right? Can we do it differently? And there is, I believe, there are printing techniques emerging. These are traditionally for flexible electronics. Transfer printing, among our research here, we do a part of it, a little bit of this somewhere, always. So let me talk a little bit about that. So once I got to NUS in Singapore, I proposed a program to look into this. So this flexible hybrid electronic systems. So as I mentioned, the phone with its rigid form factor with all its components integrated this way. Very, very impressive. But you can see what changed when you went to a smaller form factor, like the Apple Watch. Packaging technology took over. A lot of these are shrunk in a different way. Transistors didn't shrink, but the way you combine them did, right? So I believe that going forward, you may see things like that things go flexible, go in a different substrate, printed. And that may be the way to go, right? To combine the next way for innovation. So, but it's not extreme forms of flexible electronics. So Professor John Rogers, he'll be a faculty here at UIUC and now in Northwestern. So he pioneered a lot of work on electronics, Skinlike electronics. Fantastic. It's amazing work. I've read a lot of his work. It's amazing that they could make systems like that. Or Professor Takao Someya, University of Tokyo, he made basically an LED that goes on a skin. But that's not what we're talking about, okay? And the reason for that is because these are great, fantastic ideas and breakthroughs in material. They are still system-wise very limited, right? You don't see a battery here. You don't see any other power sources on this thing. And there's always a reliability issue. As a tattoo, it's fantastic. But it illustrates an innovation, the innovation to be able to thin materials down to a point where it's completely flexible. So, but what we're talking about is more complex systems that look like that, okay? So these are complex hybrid flexible electronics, immo electronics. So electronics doesn't need to be just on 2D. It can be molded into 3Ds, right? Like for example, in this case, for instance, by DuPont. And then how do we make high-performance chip on plus new non-standard substrate? And this is a vision of General Electric where they could build a patch with RF, communication circuits, microfluidics, basically digital signal processing, battery, display, everything. So no way it's going to be in a skin form because the system is too complex. But it can still be flexible. It can still be molded in different forms. And that's what we're talking about. So with that, we started a program called Highfast, which is Hybrid Integrated Flexible Stretchable Systems. Basically, the unique part of it is that we brought together 3 areas: material innovation, component integration, and then system and circuit design together, to work together. Okay. See, the thing is, circuit guys hate working with material people. The reason for that is because they always say that nothing is reliable. They are always waiting for that material to come so they can make the circuit, but after they make the simulations, the circuit never gets built. Okay, so this is one way to build a program where I say, okay, we set all expectations right. Things are not mature. Everybody sit down at a table and say, we're going to build something together. There's no compact model, so you need to fudge it for the circuit designers. And material guys, none of those 1Z, 2Z things. It needs to be reproducible. And we get them together to work together on this one. So that's the program. It's interesting because you get to basically get a microcosm of what actually happens in a chip manufacturing environment happening in school. So there are students that are working on those problems. Okay, so I'm going to introduce to you a few of those projects within the program. But before that, these are the 16 professors that are working on this, on this project, each of their team, and they have different expertise. So we have folks, myself, working on rigid devices, biomedical devices, neurotechnology, and the application side, RF, MEMS, magnetics, compact modeling, materials. So it's a mix, okay? A mix of background, a mix of personalities. So we have also industry partners who are interested to understand what we're doing. So they join us as a core partner, injecting their view on what the technology should be. And these are some of our industry core partners, as well as funders from overseas. Okay. Now, some of the projects that we're working on, for instance, is this. One example is this soft microtubular sensor for wearable application. Basically, Prof. Lim worked out a way to make, so instead of microfluidic in the negative form on a matrix, he made tubes. And we are currently looking at how to weave these tubes into sensors that are wearable, so they can be used as pressure sensing on your body. This is another project, myself with Prof. Yu, working on a body-coupled network wearable device. So one of the biggest problems is with wearable devices is the ability to power those devices, right? So you could be generating energy in your shoe, walking around harvesting energy, but how do you get the energy to your phone, which is in your hand? Nobody wants to trip over a wire that runs through your pants and up your shirt. So what we're experimenting here on is how do we use the parasitic network with the body and the environment as a weakly coupled system to transfer power. And you can enhance that by enhancing the conductivity of your body. And that doesn't mean that you're going to eat more iron, but it means that you can put conductors on your shirt, right? As easy as something like that. Okay. So we're working on interesting. So it's not all about wearable technology. So here, I think Prof. Yang in the group is working on basically a terahertz array source. So terahertz radiation is very interesting because it actually resonates with the molecular vibrations of chemicals. So you can use it for chemical sensing. So why is this wants to make it inflexible? Well, it comes in that form. So he found out through spin Hall effect that it can convert incident laser beams, laser energy, to terahertz radio waves. And you can make this into an array and lining in instruments, in semiconductor instrument in the room for various non-invasive, basically detection. And then Prof. Guo here and I are working on, for instance, flexible radars for gesture sensing and fall detection in a building, right? Oh, sorry. And then, of course, there are some, this is a large area skin conform natural interfaces. We're also circuit and system designers working on how to basically overcome basically misplacement of sensors in the body that still continue to track and to build basically batteryless operation. So these are chips that harvest energy from the environment. Okay. Okay, so that brings me to some of my projects. So I look at integration of new materials and new devices. And one of the areas I'm looking at is soft electronics. So one of the projects that I'm working on is I'm building an electrocardiogram for an activity monitoring. So basically sensing of the vital signs of the body, but also the activity of the person, right? So this work being reported here is just the ECG alone. So what's the motivation? Well, the problem is this. So doctors sometimes like to know, what your heart is doing when you're discharged from the hospital, right? So they want to track what happens, and one of the ways to do it is to measure your electrocardiogram. And systems that today are quite bulky, and we're moving towards something lightweight. And we're building systems that look like this, much smaller, basically less uncomfortable to wear, that can actually be stuck to your chest for longer term monitoring, right? So what's so special about this? Well, we use this as an example as an application to illustrate some of the challenges of integrating different materials. So this is a patch that we built. It's not that difficult. It consists of a chip on board of 7 by 7 millimeter squared. It's built with a 180 nanometer SOI technology on this board. It's powered by a coin cell battery. Obviously, we can switch it out to something fancier, but we just did this and then the unique part of this is that the patch, the interconnect is made out of liquid. It's made out of liquid metal, all right? And the electrodes are made out of a soft carbon composite. So it's not, it's a conductive material made out of carbon being beat into a silicone. So I'm going to talk about some of the features of this patch. So design-wise, the chip itself sits on a board. As I mentioned, there are two parts to highlight. One is the low noise amplifier, which is CCIA. Now the amplifiers basically rejects undesirable offsets or basic variations on the skin due at the electrode, right? So this is the amplifier design. Also important is a low dropout regulator. This low dropout regulator basically allows the circuit to continue to function while energy is drawn out of the battery, right? So these are the two main components that are there. There's an ADC converter, which I'm not going to talk about, but this whole integration is done on a board. So the chip is on one side, on this side, the top side, on the back side is where the pads are, right? And this is rigid, so no surprises. The amplifier works at 50 milliwatt, okay? And so here comes the new material, right? So this work with a flexible, stretchable interconnects is done a lot. So Professor John Rogers has pioneered a lot of this work. Now others have pioneered composite material that are conductive. So we decided to try with liquid metal. And the reason for that is because it is one of those conductors which have the lowest resistivity, right? But it has one of the biggest problems. It's not solid. That's the problem, right? It's not a wire. It's a channel. So how do you integrate something that's liquid with something that is solid and hard? That's the challenge. So the conductor we chose is Gallium. Now I'll talk a little bit about that. So liquid metal, you know, mercury. Mercury is well known. It's poisonous. Don't use it, right? There's another one which is very popular. It's gallium. Gallium is not so poisonous. It can irritate the skin, but its melting point is at 29 degrees C. So at room temp, it actually changes between solid and liquid. Not a good thing. But if you were to introduce indium and gallium into this, basically the melting point drops down to minus 19 degrees C. So it stays liquid for most, unless you're trying to monitor yourself at minus 19 degrees C. There must be something wrong with that, right? If it's sub-zero. So we chose this material. And the interesting part about integration is we molded the entire chip into PDMS, which is silicone, right? So effectively it's encapsulated. And then we create these channels where we inject the Gallium liquid metal in to interface with the pads. So the pad design is very important because these channels, they can't be too small. They're limited because you're actually getting fluid through the system. So it has to be designed in a way that there's a bend. Just imagine if it terminates at the pad, effectively you have an air bubble that kind of get trapped there. You never have a connection, right? So that's another interesting part of the integration. So if you look at it, the key is designing the pad such that it interfaces well with reliable pattern of the microfluidic structure. Now, it's kind of neat because we tested this against a mock-up in a rigid form. And the key message of this slide just says that the rigid package and the stretchable package performs identically. No issue. Of course, the flexible package has other interesting properties that the rigid can't achieve. And these are, you can bend it, stretch it, and it continues to function. So it's very robust, okay? And even we soaked it in water. We haven't boiled it yet, but we are going to do that. So this, the board itself now becomes a packaging solution. And it basically inherited functionality. And that functionality is encapsulation on top, right? So that is the interesting part of this integration. So we tested it on actually the the postdocs tested it on themselves, and it works, okay, and it works well. And you can see that compared to a wet electrode commercially available, it performs comparable. So there's no issue. So the next thing we're working on is activity monitoring, respiration activity. So chest activity when we breathe. So we would like to correlate that to ECG as well as motion of the body. So we are slowly building up systems where we collect more and more vital signs, and they're all co-integrated onto this flexible board. All right. So another material we're working on, just to illustrate the example, is moldable triboelectric nano generator. So triboelectric is a fancy name for static electricity. And it just means that when two dielectric, 5 minutes more, okay, yeah, so I'm going to run out of time. So as the two materials meet, they create fixed charge that are then transported out through a conductor, right? So we made this same thing. So basically, we take the same PDMS, same as before. So instead of injecting this liquid metal into the silicone, we beat the liquid metal into the silicone mix itself, right? So now the whole silicone is conductive. That's the thing, okay? And then we added basically a sacrificial material, which is nothing more than table salt, which we then boil it out to create pores within the structures. So it looks something like that. This is the material. These are the pores. You can see some of the leftover salt that's in there. So these material, the reason why it's black is because that's oxidized gallium oxide that forms in the material itself. And that's what it does. So basically, when you compress this material, the pores touch within the material itself, and it generates basically charges within it. And these charges are then mirrored into a conductor on the outside, and then carried on as current. Okay. So we could get about 80 volts, and currents about hundreds of nano amp, right? Depending on the size, it can even go up to 100, basically in different modes. I'm gonna, oops. So we molded it into a shoe, a sandal in this case, and then it can track gait as you walk around. Basically, walking versus running, different signal could be used for harvesting some energy. So that brings me back to this chart. So that's some of the research I've done. So back to this chart about this convergence. Okay. So the point I want to make is, to allow for this new technology to happen, we will probably need a new kind of fab. Right? Today we are very well familiar with semiconductor-based manufacturing. A new kind of fab where there's a mix of semiconductor-based equipment as well as these new materials integration tools. For instance, nanomaterial synthesis, contact printing bay, high accuracy pick and place. So these tools hopefully will combine and converge as a new manufacturing capability. Okay. So with that, I'd like to say that, back to this one chart about convergence. So I shown that basically convergence basically is really innovative integration where the whole is greater than the sum of its parts, right? And I think, I was just looking up, NSF back in 2016 have 10 big ideas. Among the 10 big ideas is this convergence research, to bring areas that are very different together to solve big problems. Okay, and so I think the trend in research is going that way, that we're going to bring. It's many forms in the past. It's called interdisciplinary research, multidisciplinary research, but now convergence, meaning different ideas, different approaches coming together, and we need basically a new integration to enable this. Right. So with that, I end my talk, I think. Yep. Thank you. Yep.
Thank you very much, Aaron, for this very futuristic talk. Is there some questions?
Yes. Yes. How
So you talked about
Mhm. Yes. Yes. Copper? Yeah, so copper is still one of the best conductor of heat. So okay, let's take a step back. The question is, besides copper, is there any other metal out there that we can use as interconnect that could conduct heat? Yeah, there is, but it's a cost issue and it's an integration issue. The reason for that is because CMOS is very sensitive to certain kind of metal. Gold and silver is a problem because they are dopants. They're bad dopants or defect creating sites. So even for copper it is. And today the resistivity in interconnect is dominated more than 50%, not by the copper, but by the barrier that surrounds the copper. So that the barrier, the barrier that stops copper from coming out of the wire is actually the biggest problem. So, and to overcome that, what has happened is industry has moved towards certain kind of material that don't diffuse as much out. So one of them is cobalt. So today I think they are trying cobalt interconnect, at least for the denser lower levels. And soon there'll be metal like ruthenium, but ruthenium is super expensive. So there are definitely options, but the way to solve it is this. The resistivity is the issue, is really the barrier. Now the heat part, same thing. Yeah. So is there, so the answer is it's an engineering problem. There's no new materials. Yeah. Yes.
So I just wondered, does liquid metal, is that an answer to
Yeah.
these drill holes and just fill it up?
Yeah, but they're expensive. Yeah. So that's the cost issue. So again, the engineering solution, yes, you can create microfluidic channels under the chip, pump the liquid metal through the system, you'll cool the chip down. But my son is buying a new gaming machine where he has a liquid cooling system on the outside. I was thinking, man, that burns more energy than the chip itself, probably, right? The mechanical system running it. But same thing, if you run that, the liquid metal is expensive. So it's not a cost-effective solution. But it's a good engineering solution, but it's not cost-effective.
Other questions?
Yes.
I have to ask another question.
Yes.
I saw your center, and you had this very group laid out.
Yeah.
But there's one glaring absence.
Yeah.
No photonics.
Yeah.
Where is the? We hear that the optical interconnect is an answer.
Yeah.
It's getting closer and closer to the
Yep.
chip.
Yeah.
Where does that come into the scheme of hybridization?
Yeah. It's a good question. There's no photonics because I think the photonics guys are too busy getting into this. They're getting too much money. That's the answer is yes, we welcome photonics people in. Indeed, we envision to have a photonics a section in. The reason for that is because photonics communication is right at the right size scale, especially for the die size of anything greater than 10 to 30 millimeter. Because below that, the electrical interconnect is more efficient. So indeed, yeah, that's right. Now, of course, doing it on flexible is not trivial, right? Because those plastic stuff do not have the refractive index differences that on silicon dioxide and silicon nitride has. So it's a different type of problem. Yes, but we do invite.
It was more of a rhetorical, not
Yeah, yeah.
More,
no. No, it's a very fair comment. Indeed, indeed, the people who working on photonics are too busy and too rich. That's the true reason. But my excuse is that it's hard to to do.
One more question. Yes.
Yes.
You mentioned the industry trying to add memory and processor together.
Mm-hmm.
So the foundry company wants to do this, and so as the memory company wants to do this package.
Yeah.
So which side do you think has more advantage?
More advantage. So it depends on which one has more cash. So okay, to be serious, I think you're right. So the funny, there are two terms out there, right? There's embedded memory. That's what logic guys tell them that they want memory to be embedded with logic. That's called embedded memory. So you heard about MRAM and that kind of stuff, right? The memory guys say compute in memory. So they say they basically want the memory devices to do some of the computation. So there is actually there are differences. It's not the same actually. The compute memory has some non-von Neumann type things to it because the compute architecture is different. You can't do all types of computation. The embedded memory is really basically how do I supplement the cache memory. So today you have level 1 cache, level 2 cache, which are all SRAM, level 3 SRAM. How do I bring new memories in there, and how deep do I bring it in? So do I bring it all the way to replace SRAM? For instance, today magnetic memory, which is a spintronic memory, has high level endurance. So they can follow with as quickly with, they can actually last as long as the switching MOSFET, because some of the memories can't. You can switch them, you keep switching them, they start to fail. They don't last. And so magnetic memory have this property, but they're big, they're huge still. So people are still looking at how to scale them down. And the excess speed wise has to be faster than SRAM, which is hard to beat because SRAM stores their charge in junctions, which basically have a push-pull thing. So, but people working on the systems are trying to move those memory in. Why? Because these memory are non-volatile. That means that the system can shut down, and then we don't have to move that data back to the hard drive, right? And they can stay there for a while. So that's the motivation. So the answer to your question is it depends on what the market is, which is another way who has the money, right? If memory companies say that they found an application that a lot of people want it and it's compute memory, yeah, they win. But today, people have been working on embedded memory for a long time in logic side. Okay.
Thank you very much. We have to stop here.
Thanks.